Okay, so we'll be starting simple harmonic motion. So simple harmonic motion can simply be defined as a special type of motion of which the oscillatory motion in which the restoring force is proportional to the displacement of the at the mean position. Now, periodic motion, also known as oscillatory motion, this is the type of motion in which a body moves back and forth repeatedly at the mean position. So the best example we can give is a pendulum bob. The pendulum bob can move back and forth at a certain position, and that position is known as the mean position. So to give an example, an illustration, we have a pendulum bob here. This bob can move in all these positions back and forth. It can go in this direction and it can go backwards like that. Now, this position, which is known as the mean position, why is it called the mean position? Because this is the position at which this bob or object attached to the string is going to rest when this thing is not in motion. So that is known as the mean position, also known as the resting position. So in simple harmonic motion, mainly we're going to focus on a spring. So we have a spring which is acting in the horizontal. This is our spring. Now to this spring, we attach an object. Now, let's say this object has a certain mass, of course. So once the string is resting, not string, sorry, the spring, once the spring is resting, at this position, this is what is known as the mean position. As it is resting, this is the mean position. This string can either be compressed or stretched. So let me just illustrate the two. So if it is compressed, it will look something like this. Let me just extend here. If it's compressed, of course, you know that to look something like this, for example. So it has been compressed. Then if it is stretched, why am I drawing a straight line? If it is stretched, to look something like this. Okay. So same spring, mean position. So this is your mean position here. Here it has been stretched. Here it has been compressed. Now, you know that once you compress or stretch a spring, and you let go, what will happen is that it will vibrate back and forth. Like we said here, that's a type of, where is it, back and forth. It will vibrate back and forth until it comes back to its mean position. Now, the process of vibrating back and forth is going to have a certain force, and that force is what is known as the restoring force. The force in which causes an object to come back to its original position after repeatedly moving back and forth. Now, we're going to talk about the displacement from the mean position. So we can say this is you can say let's use y, displacement y. This is also another displacement here, y, from the mean position to the maximum point where it has been stretched, from the mean position to the minimum point where it has been compressed. So since we're saying that the restoring force is proportional to the displacement, then we can easily say force is equals to ky. Or to start with, you can say force is equals to negative ky, depending on the two, depending on whether it is being compressed or being stretched. Now remember, it's proportional, meaning that it will have a certain constant. So since it's a proportion, we can say force is proportional to the displacement. But since it's a proportion, we can change this to an equal sign and we bring in k. So that's where the k is coming from. Now, if we have that, here's what you need to know. You need to know that k is what is known as, so k is simply the spring constant. Spring constant. So every spring has its own spring constant depending on how the spring is. Now, what are the units for this spring constant? Not constant, sorry, constant, spring constant. So what are the units for this constant? Since force is equals to ky, we can make k the subject of the formula. Hence, k will be equals to F over y. So we can simply say k is equals to F over y, force over displacement. So that is Newton per meter. So it has the units Newton per meter, like that. Okay, I hope it makes sense. So now, from there, I want us to talk about position, which we can just use xt. Position, here we can use velocity, vt, as well as acceleration, at, these three things. So if you have a function in terms of position, xt, or the function of x with respect to t, x is representing position. Now, position is talking about a particular displacement. And we know that displacement is measured in meters. So position, in other words, can be displacement. So displacement, remember, it's a displacement from the mean position to the point where the spring has been either stretched or compressed. So position is a mean position. Given a function of position, and you want to find a function of velocity, we have to apply some calculus and we have to differentiate. Same thing, if you have a function of velocity and you want acceleration, you have to apply some calculus and differentiate. So the reverse will be integration. So you have to integrate. Again, from this to this, you have to integrate. Okay. So why are we bringing up all this? And the whole purpose of bringing up all this is so that you understand there's something that will be bring out. So to start with, let's call this equation 1. We'll use it in the near future. So now that we have that information, let's look at what will happen. Given that you have a function of position, for example, how can you get a function of acceleration? We know that position is x. You have x. What we want is acceleration. How do we move from x to v? We have to differentiate. Now, to differentiate, we're simply saying to get v, so let me say v, how do we get to v when you have x? We have to differentiate. So if that's the case, we have to find the derivative of x with respect to time. Differentiate x with respect to time, you'll get velocity, like that. So now that we have velocity, how can we move from velocity to acceleration? Well, to move from velocity to acceleration, we have to differentiate, meaning that we have to differentiate this function. So to get to acceleration, we have to differentiate velocity. So differentiating velocity, velocity is the same as dx dt. So we're differentiating dx dt, hence we're getting the derivative, this one here. What does this mean? This simply means that you've differentiated the function of position twice. So we've gotten the second derivative. When we say second derivative, it means that we differentiated once, we have dx dt. If we differentiate it again, we'll have this expression that we have here. So why is all this important? So let me show you. So now that we know that acceleration is equals to the double derivative of displacement with respect to time, how does this help us? So I hope we remember that. So picking up this formula that we have here, we can easily say force is equals to negative ky, of which y is the displacement, k is the spring constant, F is the restoring force. According to Newton's second law of motion, it states that force is a product of mass and acceleration. So we can say since force is a product of mass times acceleration, according to Newton's second law of motion, we can substitute here where there's force, we'll put ma. So ma is equals to negative ky. That's what we have. If that's the case, let's put everything to one side. So if we put everything to one side, we're going to have ma plus ky, everything is equals to 0. Now, remember, we said acceleration, according to the expression that I just showed you, acceleration, a, is equals to the double derivative, which is the double derivative of position. So here where there's acceleration, we're going to substitute with this double derivative, so that we have m d squared x dt squared plus ky is equals to 0, like that. Then from there, we are going to divide throughout by mass. If we divide this by mass, we remain with the double derivative. Divide this by mass, we're going to have k over m times y. like that. Then divide 0 by mass, you still get a 0. Now, this is when we're going to bring in the angular frequency. Angular frequency is given by the square root of k over m. So, angular frequency, so we can say since angular frequency is equal to the square root of k over m, this. Then here we have k over m. So how can we write this expression here? We know that since it's equals to that, we can introduce, we can square both sides so that we have the square of the angular frequency is equal to k over m, meaning that here this can change so that we have the double derivative with respect to time plus k over m. We just replace it with omega squared y is equals to 0. Okay, so just for the sake of reference, let's use this as our equation 2, and let's use this one now as our equation 3. We're just listing them down now. Okay, so we can use this one. Okay, that is fine. So now let's break down exactly what is happening. What is angular frequency? Where is it coming from, and how can it be used further? So let's break it down. So we said there are three things: position, velocity, and acceleration. These three, of which you can abbreviate them as, remember position is the same as what? Displacement. So position with respect to time, velocity with respect to time, acceleration with respect to time. So these are the three functions we're looking at. Then we said that if we want to find an expression for velocity, if you have position, what do? We differentiate. Calculus. So we differentiate. If you have velocity, you want acceleration, we differentiate. We did this in kinematics. Differentiate. The reverse is integration. So we integrate. Again, the reverse is integration. We integrate like that. When you differentiate a function, what you get is a derivative. Just like when you add the two numbers, what you get is a sum. When you subtract, it's the difference. When you multiply, it's the product, just like that. So when you differentiate, what you get is known as a derivative. When you integrate, what you get is known as an integral. So tutorial sheet question. Let's go to tutorial sheet. Let's take an example. Please write down question. Which one? Write down question 3. So tutorial sheet question 3. Question reads: the position of a particle. The position of a particle. Not this particle. Moving along x-axis is given by x is equals to 10t squared minus 5t, where x is in centimeters and t is in seconds. So the first question is, what is the initial velocity? What is the initial velocity? Part B, find the maximum distance. Find the maximum distance, the body moves to the left of the origin. Yeah, so that's the question. Now, if you look at what we've been given in the question, we've been given an expression for position. We've been told that the position of the particle is given by a function of x with respect to time. Is that okay? So since we have a function of x with respect to time, the first question is asking for the velocity. So what do we do with that function? Do we integrate or differentiate? Are we integrating or differentiating? Differentiating, right? So remember, differentiating position gives us velocity. So here's how we can present it. You can say, question A, so velocity is equals to the derivative of position with respect to time. So in other words, we're saying to find velocity, we have to differentiate position. We all know how to differentiate. Or should I say you've forgotten? What happened when you were learning this topic? No, you did it last semester. Okay, let's do it. So, remember, position, the function for position is this one. X is equals to 10t squared minus 5t. So, to differentiate a function, you have to say the power of the variable multiplied by the coefficient. Then from the power, you subtract 1. So in other words, we're saying 2 times 10 from the power, subtract 1. 1 times 5 from the power, subtract 1. So velocity v, what is the power times the coefficient? We have 20t. So now the power of t is what? 2. So it will be 2 minus 1. Here we have 1 times 5, hence we have 5t, 1 minus 1. So power times coefficient, from the power, we subtract 1. That's what is happening. Is that okay? 2 times 10, then from that power 2, subtract 1. 1 times 5, then from that power 1, subtract 1. That's what we're doing there. So now, since we are looking for the initial velocity, before we do that, we can see that v will be equals to, this will give us 20t minus 5. Remember, 1 minus 1, 0, t to the power 0 is 1. Anything raised to the power 0 is 1, right? So this is our expression for velocity. But we're looking for the initial velocity. What does that mean? Time is what? Initial velocity, before you start anything, you start at time what? 0. So since we're looking for initial velocity, let's write it. We can say, since we want the initial velocity, since we want initial velocity, then t is equals to 0 seconds. So just substitute where there's t, put a 0. Hence, velocity initial is equals to 20 multiplied by 0 minus 5. So this will give us 0 minus 5. So v is equals to negative 5. What are the units? Position is measured in centimeters, time is measured in seconds. Hence, the units will be centimeters per second. Why is it a negative? Yes, my friend. No. It's in the x-axis. It's there in the question. It can't go down. We're in the x-axis. So why is it negative? It's going to the left. That's why the key is. Where is it? You didn't write it somewhere. It's not there. It is here. So this object is going to the left-hand side. Is that okay? Now remember, this is position we're talking about. So since it's going to the xy plane, look at this. So if something is going to the right to have a positive velocity, if it's going to the left to have a negative velocity. That's the reason why the velocity is negative. So now, at the original position, when time is 0, the velocity is negative 5. Okay. Any questions on that one before we go to the next one? That one is fine? Okay. Let's move on. Find the maximum distance the body moves to the left of the original position. Okay. Now, we have to remember something. What's the expression for velocity that we just moved? The expression, before we substituted t, we said, where is it, my friend? V is equals to 20t minus 5. Is that okay? That's the expression I'm talking about. V is equals to 20t minus 5. This is what we got after differentiating this guy. So part B is asking for the maximum displacement. The maximum displacement. Meaning we first have to find the time. So here's something that we need to know. Maximum displacement, final velocity will be equals to 0. Do we agree? Think of it. Maximum distance or displacement, the velocity will be equals to 0. Explain. Where it is supposed to reach, going to reduce its speed and become zero. That's correct. As simple as that. Remember, when you are going to a certain destination, when you arrive at that destination, do you continue moving? You've arrived. What do? You stop. So since you stop, your final velocity will be what? 0. So we can say velocity is equals to 0 at the maximum distance. Wherever you are going, once you've arrived, the maximum distance, your velocity will be 0 because you come to rest. So if that's the case, let's find time. Remember, we have an expression for velocity, that one, which is just on top there. So we can find how long it took to reach at that particular maximum distance. So we're going to say, we're going to substitute v with what? 0. This is equals to 20t minus 5. So this 5 can cross the cosine. Then we have positive 5 is equals to 20t. Divide both sides by 20, hence t is equals to 5 over 20, meaning that t is 1 over 4, which is just the same as 0.25 seconds. So this is how long it will take to reach the maximum distance. Now remember, we're not looking for maximum distance, we're not looking for time, we're looking for the maximum distance itself, measured in centimeters. Do we have a formula for distance? Grace, do we have a formula for distance? Where is it? Which one? My friend, what's your name? Dollar. Your name is Dollar. The same dollar. Okay. So what's your name? Kwacha? What's your name? Nick? Nixon. Oh, I thought maybe it's Dollar and Kwacha. Okay. So no need of going to the equations of motion. We have the formula for distance. This one. Remember, this is the formula for what? Position. It's also for what? Displacement or distance. So to find the maximum distance, just use the same formula. We can say, since the maximum distance can be given by the formula x is equals to 10t squared minus 5t, like that. Because now we have time. So just go ahead and substitute where there's t. What is the time? 0.25. So x will be equals to 10, 0.25 squared minus 5, 0.25. So let's calculate the function for distance. What are we getting? So we're getting negative 0.625, is it? So as a fraction, that is just, is it 3 over 8 or 5 over 8? 5 over 8. So negative 0.625 centimeters or negative 5 over 8 centimeters. That's the same thing. Now we know why it's negative, because it's the distance going to left hand side. That's why it's negative. I hope that's fine. Any questions so far before we continue? So this is one way in which they will ask you questions on this. Okay, let's continue from where we ended last time now. We're looking at angular velocity. Let's look at what angular velocity is. So we need to define these terms. Angular velocity, angular, or let's call it angular frequency first. Angular frequency. So angular frequency, the symbol that is used is omega. Omega. Remember, we're just breaking down the notes. I already sent you the notes. So we're just trying to break them down. So let's start by saying angular frequency is measured in radians per second. So measured in rads per second. A rad or a radian is just a measure of a certain angle. Just like we measure degrees, you can also measure angles in terms of radians. So the quantity omega is given by the formula the square root of k over m. The quantity supposed to be quantity. The quantity omega is given by, so omega, square root of k over m, where omega is the angular frequency, k, what is k? What kind of a constant? Spring constant. So spring constant. What is m? Mass. M is just a mass. So this is a formula for angular frequency. The next term we're going to look at is amplitude. Amplitude. So amplitude, you use the symbol A, capital A. What does amplitude mean?
I think amplitude is the maximum displacement when it's maximum distance from
Rest. Which type of rest? Where are you resting?
when the spring is resting before the motion begins. So it's the maximum distance from zero to that maximum distance where the spring begins.
Can reach by in terms of stretching and compressing, isn't it?
Yeah.
Okay, let's use the term for a wave. Yeah, that's correct. So let's define it this way. Amplitude is the maximum displacement from the resting position. So maximum displacement from the resting position. Maximum displacement from the resting position to the highest point of a wave. So it can also be referred to in terms of a wave, but in simple harmonic motion, you can talk about the mean position. So the resting point is also known as the mean position. Okay, next, time period. What is period? It's time, yes. So how can we define period? What is time period? Time taken to do what? Not situation. It is not a situation, my friend. So let's define it this way. Time period, the symbol used is capital T. So time period. We can say the smallest interval of time. The smallest interval of time after which the motion repeats itself. So just write it down, then we will try to elaborate. So the smallest interval of time after which motion repeats itself. Remember last time we defined this type of motion to be repeatedly back and forth, right? So think of this, think of a pendulum bob. This is our pendulum bob attached at this point. This bob, once you, remember the resting position is here. Once you let it rest, it will be, of course, going straight down due to gravity. Once you let it go, what happens? It will go in this direction to a certain point here. If it goes in this direction, what happens? It goes back again, right? So I'm saying the smallest interval of time at which the motion repeats itself, meaning that it will go 1, 2, then once it starts going back, then it's repeating itself. So in other words, we're saying the time taken to complete one oscillation. One oscillation is not one swing. This is half, then when it goes back to its original position, that is now 1. Is that okay? Yes. So let's just use the letters, for example. This is A, this is B, this is C. So for one complete revolution, it has to go from A to C, then back to A. Not from A to C, that is just half. Is that okay? Okay. Next term, frequency. Let's look at frequency. Okay, before we do frequency, let's just do this. On the same time period is equals to 2 pi over omega. Period is equals to 2 pi over omega. 2 pi over omega. Like that. Meaning that if this is the case, it means that period is equals to 2 pi the square root of m over k. Now, look at the difference. Omega, according to this, omega is k over m, right? But here we have m over k. Why have we swapped them? This is what is happening. Remember, we have period is equals to 2 pi over what? over omega. Now, what is omega? Omega is the root of k over m. Is that okay? So, since these two are dividing, this is what is happening. We have 2 pi divided by the root of k over m. When we're dividing, what we do, we multiply and reciprocate m over k. That's the reason why period is 2 pi, the root of m over k. So don't get confused. So why are we doing all this? The idea here is that if you're finding period, if you have been given omega, you go ahead and find it. But if you don't have omega, you have mass and the spring constant, and you have to use this. So don't confuse this square root and this square root. I hope you get what the difference is between the two. Okay. Next term, we said frequency. Who can define frequency? Frequency. Or rather, the number of swings. Remember, one swing is when it goes and back, from A to C and back, right? So the number of swings in 1 second. Let's define it that way. The number of completed oscillations in 1 second. So, frequency. The number, so we use a small f. You can say the number of oscillations. Number of oscillations in 1 second. Frequency is measured in what units? Are you sure? So frequency is measured, usually has 2 units. The first one is the common one, hertz, symbolized as Hz or per second. Per second. 1 over time, that is frequency. So since frequency is 1 over time, means that frequency is 1 over period. So frequency, F is equals to 1 over period. If this is the case, just on this part here, if we decide to make frequency the subject of the, period, the subject of the formula, you have another formula for period. So let's go back to period, give it another formula. Period is equals to 1 over frequency. That's the other formula for period. Period is equals to 1 over frequency. Okay, so if this is the case, another formula for this guy, for frequency will be equals to 2 pi, the root of k over m. The root of k over m. Have you seen that we've gone back to k over m and not m over k? Why? Because it's the reciprocal. So again, if we divide, you get the reciprocal. That's why we have k over m. Okay, something else we need to talk about is known as the phase angle. Phase angle. We usually use the symbol phi. So this is called, you can say this is called the phase of oscillation at a time t. The phase of oscillation at a time t. Phase angle is equals to omega t plus initial phase. Phase angle is equals to omega t plus, which one can you use? You can use a naught to represent initial. Okay, we are already tired, I can see. I hope you have space where there's amplitude. I want to give you two formulas. Remember, we talked about, before the first example, we talked about velocity and acceleration, right? So under this guy, oh, it's fine, you can leave it. Let's just say the final thing, we'll just say velocity. Yeah, this angle. It's the same thing. How can you put this? Think of this as velocity. Remember, kinematics. V is equals to ut plus, is it ut? V is equals to at plus u, something like that. Or V is equals to u plus at, is the same thing, right? Yeah, so this is representing a final phase. This is representing time. This is representing the initial phase, just like initial velocity. But it's not velocity, it's actually a phasor. We'll look at it in detail. For now, I'm just presenting the formulas. We'll come back to it. So it's just a way of finding the angle. So how do you find the angle? You need two things, the initial phase, the angular frequency, as well as time. So since it's an angle, it's measured in what? Radians. Radians. Yes, where is the degree coming from? Remember, angular frequency is measured in what? Radians per second, no degrees. You like degrees, eh? Okay, so let's talk about velocity. Let's just say velocity and acceleration. Velocity and acceleration. So we just give two formulas for velocity and acceleration. Maximum velocity and maximum acceleration. Okay. These things are not complicated. Sorry? Yeah. No, just wait. I'll give you how to, I'll present to you how you're supposed to write it. So you can say maximum acceleration, or write it like this. A max is equals to omega squared. What is A? Amplitude. So children, A is acceleration, adult A is amplitude. So V max is equals to A omega. Yeah, that's A omega. That's it. Yeah, omega squared. So maximum acceleration is equals to amplitude. That. Guys, these things are simple. Like I said, don't be afraid of something you don't know. Grace, don't be afraid of something you don't know. Is that okay? Look at the question we're just from doing, question 3. Now that we've done it after doing the calculus, it's just straightforward, right? So let's continue making these things simple. Let's go write down question 1 in the tutorial sheet. They are simple, don't worry. I hope you have all the formulas. Question 1. A body executes simple harmonic motion. So when you say a body executes simple harmonic motion, we're saying that this body is moving back and forth repeatedly. Remember, that's the definition for simple harmonic motion. So a body executes simple harmonic motion, okay, such that its velocity at the mean position, is 1 meter per second, and acceleration at one of the extremities, and acceleration is 1.57 meters per second squared. Calculate the period of vibration. Period of vibration. So here's one way in which you can understand this topic. I can give you a task. Every formula that we've written, go and list them down, have them somewhere. Every formula from when we started, go and list them down. You see that every question you're supposed to use a certain formula. So your job is just to understand the question and know which formula you're supposed to apply. That's it. Is that okay? Let's answer the question. So we have been given two things: velocity and acceleration. So since we have been given velocity and acceleration, those are the formulas we're going to use. Velocity and acceleration. So to use those two formulas, this is what I'm going to do. We're going to say, we shall divide acceleration over velocity. Simple as that. So solution, you can say divide acceleration over velocity. Divide acceleration over velocity. So in other words, we're dividing the maximum acceleration over the maximum velocity. Hence, this is what I want to get. We're saying A max divided by V max. You see why we're doing this? So what's the formula for acceleration? It's this one here, which is A omega squared divided by the other guy, what we have? A omega, like that, according to this expression that we have here already. So now let's substitute the values. What is the value for acceleration given in the question? Acceleration of been given, this one here. So we'll have 1.57. What is velocity? Velocity is what? 1. Is equals to, remember amplitude will cancel. Is that okay? So amplitude cancels, omega cancels. You just remain with 1 omega. Is that okay? Omega cancels. Amplitude cancels. So in short, omega is equals to 1.57 radians per second, according to this expression. Is that okay? Yeah. Teresa, look lost. Is it okay? Yeah. Now, what are we looking for? Period. Let's go back to period. There's a formula which connects period and angular frequency. I've just remembered. Let's go back to period. There's a formula which connects period and angular frequency. Where is it? So period is equals to 2 pi over omega. Simple as that. So we can now say since period is equals to 2 pi over omega, then period will be equals to 2 pi. What is our omega? The same value that we have, which is 1.57. So divide the two. What do we get? Very simple. So 2 pi divided by 1.57, I'm getting 4. What are the units? What are the units? It's period. So units are seconds. What is difficult now? Please take note of the questions we are answering in the tutorial sheet. By the time we're finishing this topic this week, we should have done everything in this tutorial sheet. Okay. Next question. Let's attempt question 5. Please write down question 5. Question 5. So question 5 says the kinetic energy of a particle, the kinetic energy, let's just say the KE Ke of a particle in simple harmonic motion is 4 joules. Okay? When it passes through the mean position. When it passes through the mean position, if its mass is 2 kg and the amplitude is 1 meter. Calculate its time period. So that's what we have. So the kinetic energy of a particle in simple harmonic motion is 4 joules when it passes through the mean position. If its mass is 2 kg and the amplitude is 1 meter, calculate its time period. Okay. So for this one, we are going to start with what we've been given, kinetic energy. So we know that this guy is given by Ke is equals to half mv squared. That's where we'll start from. So half, so let's say Ke is equals to half mv squared. Now, velocity, we have the formula for velocity. Velocity is equals to what? Amplitude times omega. So, you can say Ke is equals to half the mass, where there's velocity, we substitute with what? Amplitude times omega. But remember, everything is squared because the velocity is squared. Like that. Then, since the square belongs to the amplitude and the omega, then we can say Ke, kinetic energy, is equals to half times mass times amplitude squared times omega squared. What are we looking for? Time period. So remember, to calculate time period, what do we need? We need omega. So in other words, we're saying from this expression, let's first find omega. Using omega, we're going to proceed and find what? Time period. Do we have Ke? Yes, 4. Half. Do we have M? Yes, 2. Do we have A? Yes, 1. And the omega is what we're looking for. So half times 2 is just 1. So 1 times 1 times that. So omega squared is equals to 4. Half times 2 is just 1. That's okay? Half times 2 times 1 squared is just 1. So omega squared is also 4. If you take a root to both sides, you can see that omega is equals to 2 rads per second. So now that we have this, we have omega. We can proceed and find what? Time period. So to do that, using the same formula, time period, which is T, is given by the formula 2 pi over omega. So time period, 2 pi, what is omega? Omega is what? 2. So period is equals to pi. So period is just pi. So what's the value of pi as a decimal? It's 3.14. So you just have it as 3.14. So period T is equals to 3.142. It goes on, of course. So it's measured in seconds. Very simple, my people. Any questions? Which part?
Starting from KE half MA squared.
Here.
Omega squared.
Remember, all this is squared because they're in the bracket from V. So you separate the square there and there. Amplitude is 1. Omega is what we want. Half times 2 times 1 squared is just 1. So all this is just 1. Omega squared. Straightforward. Last question, then we can call it a day. Physics-wise. Don't be excited. Let's do question 4. Question 4. So, question 4 reads, a block is kept on a horizontal table. So I'll be drawing the diagram, you write the question. So a block is kept on a horizontal table. This is our block with our horizontal table to match. A block is kept on a horizontal table. The table is undergoing simple harmonic motion with a frequency of 3 Hz. Frequency 3 per second. What else do we have? So the table is undergoing a simple harmonic motion with a frequency of 3 on the horizontal plane or in the horizontal plane. The coefficient of static friction between the block and the surface is 0.2. Remember, this is mu. So mu sub s is 0.72. Has no units because it's a coefficient of static friction. What else do we have? Find the maximum amplitude of the table at which the block does not slip on the surface. Find the maximum amplitude of the table at which the block does not slip on the surface. Okay, so we have this block which is on the table. What are the forces acting on this block? If we were to push this block, what would be the forces acting on it?
Reaction force
Reaction force, yeah?
is mg, mass and gravity. And if we push it, if we apply force, there's friction opposing motion, and there's also force.
Which force? You've talked about forces, and then you say there's also force. Which force? No, there's no restoring force here. Normal force, right? Remember, I said if this object is being pushed in one direction, you have an applied force in this direction. There's a force which opposes motion. That force is known as what? Friction. This object will always have this force which goes straight down, weight force, also known as mg. Then the force perpendicular to the surface is the normal force. Just use N. Those are the forces acting on this object. Remember, it's on the horizontal plane. So, for this object not to slip on the table, by slip we mean for it not to fall off the table, right? What should happen? The forces should be balanced. Newton's first law of motion states that an object at rest will remain at rest until the forces are unbalanced. Do you know what that means?
Yes.
Here's an example. If you have an object, you have two people, someone pushing with a force of 20 newtons, another person this side pushing with a force of 20 newtons. Is that okay? Is this object going to move? The answer is no. Why? The forces are balanced. But as soon as you increase the force on one end, you see that the object will start moving. So that for that object not to move means that the forces must be the same. So if that's the case, let's apply Newton's third law of motion, which states that for every action, there is an equal but opposite reaction. So if that's the case, we're going to say friction force is equals to applied force. For every action, there's an equal but opposite, meaning that friction is equals to applied force. What's the formula for friction force? Mu times normal, or which mu is the coefficient of static friction, right? So friction force is mu static times normal force, which is equals to Newton's second law of motion. Force is a product of mass and acceleration. Newton's third law, again, for every action there's an equal but opposite reaction, y-axis. Normal force is equals to what? Mg. Is that okay? Newton's third law, for every action there's an equal but opposite reaction. Hence, where there's normal force, we substitute it with what? Mg. So, we'll have this guy, the mu, where there's normal force, we'll put what? Mg. This is equals to Ma. Like that. I hope you understand how everything is coming up. From there, we can say mass can cancel out. Divide both sides by m, mass will cancel out. So mass disappears, meaning that A is equals to mu times acceleration due to gravity. Is that okay? Mass cancels out. So let's find acceleration. So acceleration in this case is equals to, what is mu? Mu we've been given, 0.72. So 0.72 multiplied by acceleration due to gravity, let's use 9.81. What is our acceleration? What's the linear acceleration? So 0.72 times 9.81. Okay, I'm getting 7.06. So 7.06, is it correct? Meters per second squared. That is my acceleration. But remember, what do they want in the question? What are we looking for?
The question says find the maximum amplitude.
Find the maximum amplitude. Now, there's a formula which connects amplitude and the acceleration. Yes, I gave you, it was here, in fact, it was here.
Oh, yes. It's
What's the formula? We said acceleration is equals to amplitude times omega squared, right? So what don't we have? We're looking for amplitude, right? We have acceleration. We don't have what? Omega. So let's find omega. Go back to friction. No, not friction, sorry. Frequency. The formulas for frequency. There's one formula I want you to put for frequency there. I want you to put this formula here. Omega, which one should we use? Omega is equals to 2 pi frequency. Omega is equals to 2 pi frequency. This formula is coming from this one. Remember, period is equals to 2 pi over omega. Remember this one? Do we remember this one? Now, what is period? We said period is the same as 1 over frequency, right? So where there's period, we can put 1 over frequency. This is equals to 2 pi, like that. If we cross multiply, we will see that omega times 1, we have omega. Frequency times 2 pi, we have 2 pi frequency. So we can easily find omega by saying omega is equals to 2 pi frequency. So that we have omega, remember in the question we have frequency. Frequency in the question is given to us as what? 3 times 3. So omega is equals to 6 pi. What's the value of 6 pi? What is 6 multiplied by pi? So 6 pi. I'm getting 18.9, is it? 18.9. So 6 pi is simply 18.9 Let me use all the decimals. 86 rads per second. So now that I have omega and I have acceleration, I can easily find amplitude. So this is what I want to do. We have these two guys. Remember, acceleration is equals to amplitude omega squared. Remember that? So to find amplitude, what do? We simply say amplitude is equals to acceleration divided by omega squared. So amplitude is equals to A over that. So let's divide the two. So acceleration I found 7.06. Okay. So if we calculate everything, what are we getting? What are we getting? Let's do it. So we're saying what are we getting? 0.02, right? Okay. So since we're getting 0.02, what are the units? Meters, right? So amplitude is 0.02 meters, but 0.2 meters is just the same as 2 centimeters. Simple as that. So that's our answer. And our last question, we end there. We shall continue from there. Any questions?
You had this videos like this on your